Hello, and welcome to this introduction to Corensic. During this webinar, I'll introduce you to what concurrency errors are, and teach you a little bit about the implications of those concurrency errors in your applications. I'll introduce you to our first product, Jinx, which will help you find and fix concurrency errors in your applications. I'll show you how Jinx works, and I'll show you how to use Jinx in your development environment. Now, in traditional development, sequential programming, when you ran a program with a given set of inputs, you got a predictable result every time. Same input, same output. And if you were to test those applications, you would test those applications based on a series of input that you provided it, and then test the results using traditional unit testing or other testing mechanisms. In the world of concurrent programming, you can run a parallel program several times with a given set of inputs and get unpredictable behavior. That's because the operating system, the hardware, and other aspects of your personal computer or server will schedule threads in a different manner so that you can get a different result each time you run the application. Now, a common software development and testing challenge occurs in test labs, when several machines inside of your test lab will manifest no bugs. But one machine, the unlucky machine, keeps manifesting a bug. That's because this one machine happens to have a particular thread timing that creates a bug. We'll talk about a little bit about that in a little while. Now, what you really want is if there's a bug in your program, you want every machine in your test lab to manifest that bug. In effect, you want all the machines in your lab to be unlucky. Now, the unlucky machine, where that bug happens, may have a bug only every now and then. Sometimes that unlucky machine may run flawlessly. Another time is when you have a bug that only happens in a deployed application, or even worse, at a customer site, but never in your lab. And tracking down those bugs are also very difficult. Now, sometimes a bug only happens on one developer's desktop, but not on others. And in even other cases, bugs may happen occasionally, but never consistently enough to generate repro steps so that you can cause the bug to happen consistently. That's because concurrency errors don't exactly always manifest themselves consistently. Now, a common concurrency error is an atomicity violation. Here we've got some code with shared memory that's protected by a lock that we call A. And if we look at the execution on this thread, in thread 1, if I'm going left to right in terms of the execution time, I lock the shared data, and then I go ahead and use it. I unlock it, so more execution happens. Again, I lock the data, I perform operations on the data, and then I return the lock once again. Now, if another thread wants to access that same memory area that's been protected by A in thread 1, and let's say that other thread has a particular thread timing where it accesses the data before our lock, unlock, and lock, unlock operations. In this case, our application will actually execute just fine each time because the data is being accessed in a sequential manner. Let's say, in this particular case, it just so happens that the timing of thread 2 is such that the operation on the shared memory occurs in between the lock-unlock blocks. In this case, we would have an error. It's not anticipating that another thread will come in and alter that memory. Now, concurrency errors can have grave ramifications. In 2003, the entire northeastern U.S. power grid blacked out. This affected 55 million people, caused 11 fatalities, and cost over $6 billion in damage and lost productivity. The culprit was a race condition bug that had been executing in monitoring software. Now, this monitoring software had been running for millions of hours and for over a decade without any errors whatsoever. And then one day, there was a particular thread timing that caused a race condition that caused monitoring software to fail to recognize that it needed to shut down circuit breakers. Had those circuit breakers actually been shut down, then the entire blackout would have been averted. Another famous concurrency error is the Therac 25 radiation therapy machine. Again, a race condition in this device caused an electron beam to produce over 100 times the appropriate level of radiation for cancer patients. This lethal dosage killed several people, and the root cause of the error was a race condition bug. Now, concurrency errors also have other ramifications. If you think back to the early 2000s, several code defects called buffer overruns contributed to some of the most notorious memory leaks, and security exploits in computer history. The SQL Slammer bug, the Code Red bug, and the NIMDA virus all caused billions of dollars of damage. Now, prior to those bugs actually being manifested and exploited in 2003, there were several tools in the market, Purify, NuMega, and others, that would help detect buffer overruns in code. Very few developers actually took advantage of these tools, and once the actual SQL Slammer, Code Red, and NIMDA viruses came to fruition, those tools became immediately popular. If we fast forward to today, the modern security exploit will be concurrency errors. It will be malware that purposefully attacks concurrent applications and tries to time itself in between atomicity violations and cause race conditions that could compromise systems. And so what developers need are tools that can help them detect concurrency errors at design time in the same way that tools like Purify and NuMega could detect buffer overruns at design time. Now, a lot of the best practices for finding concurrency bugs today are brute force. The first one is prolonged stress testing, running an application across multiple configurations in a test lab. Effectively, your application will occupy and consume an entire test lab for hours. You would run that application for hours or for days, hoping to flush out particular thread interleavings that cause bugs. And in coupling with that, you would also insert waits and sleeps, probably manually entering thread waits and sleeps throughout your code and trying to artificially create different thread interleavings that could potentially flush out these bugs. And the last one, at the end of the day, you just ship your applications and pray that you've caught all the concurrency bugs in them. And there is a better way. Jinx is a tool that plugs into your existing development environments and makes multi-core or concurrent bugs happen quickly, and enables developers to identify the root cause of those bugs with immediate forensics. Jinx is available for Windows and for Linux today, and it works the way you do. It integrates seamlessly into your existing development and build processes so that bugs can happen faster and so that they make more sense. Jinx is reliable. With Jinx, there are no false positives. When Jinx finds a bug, it's definitely a bug in your code. And Jinx is easy to use. Within 3 minutes of downloading, you'll be able to install Jinx and start finding bugs. And already we've seen hundreds of customers who find that Jinx is a priceless gift if they're building multi-threaded applications. So what Jinx does is it makes your code unlucky. It flushes out those hidden bugs in your code so that you can have greater confidence in your software. Effectively, what Jinx does is it accelerates the rate at which bugs manifest themselves. Instead of having to spend hours or days running your applications inside of a test lab, you can run Jinx and force those bugs to happen in minutes. And Jinx points out the cause of your bugs so that you can find, fix, and verify those errors before they reach your customers. With Jinx, you'll save a lot of time trying to track down the cause of concurrency errors in your applications. You can view demos of Jinx at www.youtube.com/Corensic. Let's talk a little bit about how Jinx works with Microsoft Visual Studio 2010. Visual Studio 2010 includes a number of new features for parallel development, including the Parallel Stacks window. The Parallel Stacks window provides a view of all your call stacks, organized by thread, in a very familiar and easy-to-use visual environment. When Jinx forces a concurrency bug in your code to happen, it positions all the threads and call stacks in your application in the debugger in the right position so that you can get an accurate snapshot of the application when the bug occurred. The yellow arrow indicates the causality of the bug, or the thread in this particular case, where the bug occurred, so that you can drill into your application and find out exactly how to fix your application. The Threads window is an old standby in Visual Studio that's been augmented and provides a tabular view of all threads in your application. Again, when Jinx forces concurrency bugs in your code to happen, it positions all the threads inside the thread window in the correct position so that you can get an accurate snapshot of your application and where the bug occurred. And the yellow arrow, once again, automatically indicates the thread in which the bug occurred. And of course, the code editor provides a visual indicator of all the elements in your code, and once Jinx forces the concurrency bug in your happen, when you're still in debug mode, you can use the code editor to step into and out of methods, and the yellow arrow lights up in the gutter to indicate the current line of code being executed. After Jinx forces the bug to happen, it automatically positions the yellow arrow at the line of code where the bug most likely occurred. Again, Jinx works the way you do. You use the tools that you already know, you use the debuggers that you already know, whether you're using Linux or Windows or Eclipse. You use all the tools you already know, and Jinx automatically forces bugs to happen and positions all the threads and call stacks in the right place so that you can use your existing tools, your existing development processes and methodologies to find the bug, to fix the bug, and to verify that the fix actually worked. Now, Jinx works underneath the covers by intelligently sampling periods of execution and exploring many different possibilities for thread timing. If you think about all these different alternate realities that Jinx is looking for, what Jinx is doing is it's looking for a particular alternate reality or thread interleaving that will cause a bug. And when it finds a thread timing path that will result in a bug, it then goes and replays it for the developer inside the IDE or debugger of their choice, whether it's Visual Studio or the command line or Emacs or what have you. And additionally, Jinx has a feature called Smart Stop, which pinpoints the exact causality of the bug. Now, in a typical multi-threaded program, when a bug occurs in one thread, the other threads may continue to run until the application stops. When a developer looks at the end state of the program, they have no meaningful information because the thread where the bug actually occurred may have faulted and may have stopped, but the other threads just kept on going. Jinx is different. When Jinx finds a bug and forces a bug to happen, it automatically positions the end state of the program in a meaningful location so that the developer can then go and find the root cause of that bug. It helps the developer save a lot of time by giving them all the information they need to quickly find, fix, and verify concurrency errors in their application. Jinx has a significant advantage over other tools. Now, first of all, Jinx is almost fully complementary to all the existing tools and development processes that you use. Jinx merely accelerates the rate at which bugs manifest themselves, and then it pinpoints the causality of those bugs. It works great with Visual Studio, with Intel Parallel Studio, and with a number of other tools that you're probably familiar with, including on Linux, things like GDB. With Jinx, there are no false positives. A lot of concurrency tools provide you with a list of potential errors, which you as a developer then need to go and figure out and verify whether they're actually an error or not. With Jinx, when it finds a bug, it's definitely a bug. Jinx also intelligently samples execution. It's not random timing intervals. Jinx is actually using a lot of heuristics and algorithms to determine exactly which sample of execution that it wants to try. And Jinx is completely operating system and application platform independent. Jinx works regardless of what programming language you want to use, what application platform you want to use, or even what operating system you want to use. Jinx works underneath your operating system in order to effectively and intelligently sample your execution, explore various thread interleavings, and force bugs to happen. And Jinx requires absolutely no changes to your source code. As a developer, you get to use the programming language of your choice, you get to use all the code libraries that your company is already standardized on or that you're familiar with. You don't have to change a single thing about your source code. All you need to do is install Jinx, enable it, and then Jinx will start finding bugs inside of your application. Jinx is available today. It's available for $1,999 in US dollars per user. There's also a 30-day trial license available and a restricted use academic and non-commercial license for those that may qualify. Visit the Corensic website for more information and also to find out whether or not you qualify for the academic and non-commercial license. In Jinx V1, we're focused on development and test scenarios, making bugs and concurrency bugs happen more frequently, pinpointing the causality of the bug, and supporting Windows and Linux on 64-bit and 32-bit platforms. Customers love Jinx. They find that when they're not using Jinx, bugs may occur in hours. With Jinx, they occur within minutes. It helps developers who are writing threaded applications immediately find and fix bugs without having to spend an inordinate amount of time hunting down the cause of those bugs. With Jinx, you'll be a lot more productive, your software will be much higher quality, and you'll reduce the risk of security errors or other errors that you'll expose to your customers and to your clients. If you have any questions, visit our website or send mail to sales@corensic.com. Thank you very much for your time.